With an anticipated market growth from $9.6 billion in 2020 to an impressive $15.2 billion by 2025, the adoption of brushless DC motors in industry is drastically increasing. These motors can be used in a wide variety of industries, such as HVAC systems, medical devices, electric vehicles, and other consumer electronics. Brushless DC motors rely on a change in electrical current around a steel conductor in order to induce a magnetic field which then rotates a spinning magnetic piece on the motor. At any given time, one phase pulls the magnets, another phase pushes the magnets, and then one phase is a floating neutral point on the motor. The main PCB was used to control the motor's speed. Once the board was fabricated, the various electrical connections were tested by displaying to the LEDs. The Hall effect sensors provided invaluable feedback to then set the speed of the operating motor. The O shape of the PCB allowed the spinning rotor to operate inside the diameter. The square-shaped board had to be cut precisely in order to ensure no friction between the rotor and the PCB. With the Hall effect mounted onto the plexiglass, the firmware from the controller was tested using feedback from the spinning rotor. This tested the buttons, display, and implemented state machine of the Hall effect sensors. The mechanical design of the system consisted of a stator with accompanying mount, a rotor with various braces and magnets, as well as the Hall effect PCB, accompanying mount, and the main PCB and assorted plexiglass. In order to mount the motor to the plexiglass provided, various parts were 3D printed. The 3D printing process displayed here was for the Hall effect mount to be stationed beneath the rotor. An additional mount was needed to lock the stator firmly into the plexiglass. Next, a water jet cutter was used to cut through the steel laminations. Scrap steel was used for test cuts, and then the actual laminations were cut on the silicon steel. The laminations were then stacked and bolted. The magnets were placed around the rotor after it was bolted. With the mechanical construction tested, the first attempt at winding the copper around the stator was completed. However, with the windings placed directly on the steel cut through the copper insulation. A 3D printed plastic bobbin was the solution, as it provided a barrier between the steel and copper insulation. Additionally, each phase was then color-coded. When assembling the system, the first step was to properly mount the Hall effect sensor PCB and main PCB to the plexiglass. With the PCBs mounted, the next step was to properly secure the stator above the Hall effect sensor PCB. The corner braces were added. Then the rotor and magnets were placed inside the diameter of the stator. The top layer of plexiglass was then firmly secured to the braces. For the final demonstration, we tested each button's functionality in regards to the motor's operation. This included powering on the motor, turning the speed up and down in terms of rotations per minute, as well as an additional feature we built in to change the direction of the motor's rotation. The operational range of speed for the motor was about 120 RPM to 1000 RPM at its upper limit. The 3D printed brace placed above the motor was used to ensure no movement occurred of the rotor on the shaft. This also promoted safer and more secure rotation when operating.